Hi everyone, today I'm going to talk about benchmark design and prior-independent optimization. This is a joint work with Jason Hartline and Alex Johnson. The main purpose of this talk is to talk about the analysis of information-restricted algorithms. What are information-restricted algorithms? Let me illustrate using some examples. First, take online algorithms as an illustration. Here, the decision maker needs to make decisions without knowing what the future is. Another connoting example is mechanism design, where the seller doesn't know the value of the agents, and she needs to design the mechanisms to incentivize the agents to review their valuation and try to achieve good outcome in equilibrium. One common thing about those algorithms is that actually it cannot achieve pointwise optimal for every possible input to the algorithms. And thus leads to the natural question, which algorithms are good and which algorithms are bad. And the main purpose of this talk is to provide a meta view of understanding which way of analyzing the algorithms are good or bad. There are three standard ways for analyzing the algorithms. I'm going to provide formal definitions later in a moment, but here, just briefly understand what those analysis means. First, Bayesian analysis. It assumes that the inputs are come from known distributions, and the designer needs to find the algorithm that maximizes the performance in expectation. And also we have the prior-independent analysis, which assumes that there is a distribution over inputs, but this distribution is not known. And the designer needs to find the algorithm that maximizes the performance under worst-case distribution. Finally, we have prior-free analysis. It assumes that the input is given by an adversary, and the algorithm designer needs to find the one that maximizes the performance in worst case. So, one main theorem we want to present in this talk is to have a formal optimization framework for the prior-free analysis and show that it is actually equivalent to the prior-independent analysis. Here is an outline of today's talk. I have given you a very brief introduction and motivation. Next, I will formally define what are those three analysis means and show that a formal definition of the prior-free benchmark optimization program is actually equivalent to the prior-independent analysis. There is a heuristic way for optimizing the benchmark, and in this talk we will show that this heuristic approach is not without loss, and we show it by solving a major open problem in the prior-independent mechanism design literature. And finally, I will summarize what results we have presented in this talk. So before the formal definitions, let's first agree on the notations. We use M to denote the algorithms and V as input, and M of V as the performance of the algorithm given input V. And given distribution F, we use the M of F as the expected performance when the input are drawn from distribution F. And we use the bold F as family of distributions and M as the family of algorithms. And now we can formally define what those three analyses are. First, for the Bayesian optimal algorithms, let's try to identify a single algorithm that maximizes the expected performance given the known distribution F. The good thing about this Bayesian analysis is that it's optimal. And the disadvantage for this analysis is that it's not robust, meaning that the algorithms that are optimal for one distribution may have terrible performance for other distributions. And thus we can have the prior-independent analysis, which is trying to identify a single algorithm that minimizes the maximum approximation factor for all possible distributions. Here, we can use the additive approximation as the approximation factor, as people usually do in the online learning literature, or we can use the multiplicative approximation as people usually do in the mechanism design literature. Both of those definitions works on our general theorem, and later in this talk, when we talk about detailed applications, we will choose the version that applies with the convention of the literature. And the good thing about this prior-independent analysis is that it's obviously more robust, but still, this still relies on the assumption that the input is stochastic. And finally, we will have the prior fear analysis. And this requires a given benchmark B. And given this benchmark, I try to identify a single algorithm that minimizes the worst-case approximation factor over worst-case input. And certainly, this analysis is robust, and it doesn't require the input to be stochastic. However, this requires the given benchmark, and exactly how good this analysis is depends on how good choice the benchmark is. So this is the formal definition of those three analyses. And one clear question remains is how we can choose a benchmark for the prior fear analysis. And more specifically, what properly makes a benchmark a good benchmark. There have been some work done for specific problems like two-server problems, which compares the performance of different benchmarks. And the goal of this talk is to provide a general approach for all possible settings. And let's first look at what's the goal of designing a benchmark. The goal is just try to discriminate between good or bad algorithms. And there are two criteria. The benchmark should not be too small or too large. If the benchmark is too small, then many algorithms can approximate the benchmark, and it doesn't discriminate between good and bad algorithms. And the same thing happens if the benchmark is too large, then no algorithm can approximate the benchmark. Let me illustrate using some examples in online learning. Here in this setting, there are m actions in n rounds, each associated with reward Vij, and the agent needs to choose an action before seeing the actual reward in each round. One intuitive benchmark is first best, which is to find the sum of the maximum reward on each round. And there are two algorithms. First is the exponential weight, which are very nice algorithms that are commonly used in online learning literature. And another is uniform random, which is just randomly picking an action in each round. You can imagine exponential weight would be better than uniform random algorithm, but if you use the first best benchmark, you can see that over worst case input, both of them have a worst case approximation factor linear in the number of rounds. So this first best benchmark doesn't discriminate those two algorithms. And the reason is that the first best benchmark is too large. Thus, this leads to our goal for designing a good benchmark, and we will formalize what does it mean for the benchmark should not be too small, and then we will try to optimize the benchmark such that it will not be too large. First, to define what does it mean to be not too small, we have the definition of the normalized benchmark. And given a family of distributions, we see that a benchmark is normalized if the performance of the benchmark is at least the Bayesian optimal performance for every possible distribution within this family. And naturally, one can think that if the benchmark exceeds the Bayesian performance, then this benchmark is naturally not too small. And a nice property that normalized benchmark gives us is that if any algorithm that achieves prior-free gamma approximation to a normalized benchmark, then this algorithm is naturally a prior-independent gamma approximation. And this is the definition for the benchmark to be not too small. Next, we will look at the criteria that benchmark should not be too large. First, we need to have a quantity that value is how large the benchmark is, which we define as the resolution of the benchmark. And given a benchmark B, the resolution is defined as the minimum approximation factor for any possible algorithm within this family over the worst case input. And why this satisfies as a good evaluation for how large the benchmark is? Also, again, look at the example in the online learning. For the first best benchmark, the resolution of this benchmark is linear in the number of runs, while widely used nice benchmark, best in hindsight, only have resolution square root of n. So this illustrates that actually first best benchmark have too large resolution, which aligns with our intuition that this benchmark is too large. With this definition, we can have our formal benchmark optimization program, which is to find the normalized benchmark that minimizes the resolution. Okay, now we have a formal definition of the benchmark optimization program. And next, we will show our main theorem, which is to say that this formal defined benchmark optimization program is actually equivalent to the prior independent analysis, that is, gamma is equal to beta. Next, I will show you how to prove this theorem with two steps. First, we need to see that gamma is upper bounded by beta. First, suppose M is the optimal prior independent algorithm with the objective value beta. And then we can define the benchmark by scaling up the algorithm M by its approximation factor beta. Then M and B are a valid pair for the benchmark optimization program with the objective value beta. This indicates that the optimal solution to this benchmark program is at most beta. For another direction, let's say M and B are a pair for the solution to the optimal benchmark optimization program with objective value gamma. And since that benchmark is normalized and the algorithm is a gamma prior-free approximation to the benchmark, this naturally indicates that this algorithm is a gamma prior-independent approximation, which suggests that the beta is at most gamma. And combining those, this leads us to the equivalent result that the benchmark program is equal to the prior-independent program. And what can we learn from this equivalence result? Originally, people would think that the prior-free program would generate more robust results than the prior-independent analysis, since it does not require the stochastic on the input. However, we show that if we have a formal definition for how to optimize the benchmark, then this formal definition of the benchmark optimization program is actually equivalent to the prior-independent analysis. One concern people may have for this equivalence is that actually in literature there exists some ad hoc benchmarks that actually generate more robust solutions. Again, for the online learning, suppose the input come from identical and independent distributions, then we can show that follow the leader is actually prior-independent optimal, means that the optimal benchmark is just scale up follow the leader. Note that there is a widely used heuristic benchmark which is called best in hindsight, and a very nice algorithm exponential weight that can actually approximate the benchmark. And if we try to compare the follow the leader and the exponential weight, we can see that there exists input to the algorithm such that exponential weight outperforms the follow the leader. and the gap is linear in the number of rows, which suggests that actually follows the leader is not very robust. So this observation leads to a major open question following our formal framework, which is to see that whether we can actually find a benchmark optimization framework that can retain the robustness of the ad hoc benchmarks, like Bayesian hindsight in the example of online learning. Now we have established what the benchmark optimization program is, and intuitively, it is difficult to calculate what is the optimal algorithm given a benchmark, thus rendering the benchmark optimization problem hard to solve. And literature have some ideas of finding the correct benchmark in some settings. And the traditional approach is to find a lower bound for the performance of the algorithm, which is the ratio between the benchmark and the expected Bayesian performance. And plug into the program, we will give this heuristic optimization. And it serves as the lower bound for the original benchmark optimization program. And note that in many settings like digital goods revenue maximization program, there exist various benchmarks such that the bound is actually tight, meaning that it is without loss to consider this lower bound. And a natural question following those work is to see whether this heuristic benchmark optimization program is without loss or not. The short answer is no. I will show you in a moment. So first, we need to solve for one of the program, which is the prior fee benchmark optimization program. And using our equivalence result, it is sufficient for us to solve the prior independent optimization problem. And what we will do is to solve it for a canonical problem, which is to sell a single item to two agents for the revenue maximization program. And we will consider the family of mechanisms to be the family of truthful, feasible, and scale invariant mechanisms. Here we have this assumption of scale invariant. Currently we do not know if the without loss or not. And as shown in Allo and Burr's 2018 EC paper, this scale invariant mechanisms are actually optimal among a fairly large family of mechanisms. And then we will consider the family of distributions as IID regular distributions. And regular is an assumption on the distribution, which is commonly assumed in the mechanism design literature. And we will not talk about this formal definition for this talk. Currently, what do we know for this problem from the literature? And we know that using the simple second price mechanisms, we can directly achieve price independent approximation factor of 2. And by introducing randomness in the price posted to the agents, we can show that the price independent approximation factor can be improved to be strictly better than 2. And previously, the best non-bound for the price independent approximation ratio beta is between 1.8 and 1.95. And what we will do in our paper is to exactly pin down the approximation factor beta. And what is the mechanism that achieves the optimal ratio? Is this very simple mechanism, which is seller will first draw the parameter alpha with the following distribution, and then the seller will offer agent 1 with price alpha times V2 and offer agent 2 with price alpha times V1. And note that since this ratio alpha is at least 1, so in any case, at most one agent will accept the offer and sell the item to at most one agent. So this mechanism is clearly feasible. And The major theorem in this setting is to see that this simple random markup mechanism is actually prior-independent optimal, and it achieves the approximation factor roughly 1.91. I will not provide the formal proof for this theorem, but intuitively, to solve the prior-independent optimization problem, we can actually just view it as a zero-sum game between the designer, who chooses the mechanism, and the adversary, who chooses the distribution of valuations. And any Nash equilibrium of this zero-sum game suggests that the strategy of the designer is optimal for the prior-independent program. And what we do is just to show that this random markup mechanism combined with a distribution over valuation forms a Nash equilibrium for this zero-sum game. So for this canonical setting, we solve for the optimal prior-independent program. It's using our equivalent result. It naturally gives us that for the benchmark optimization program, for this revenue maximization setting, gamma is roughly 1.91 as well. And to show that the heuristic benchmark is not equivalent, it is sufficient for us to provide a heuristic benchmark, suggesting that gamma hat is strictly less. And what this heuristic benchmark is, first, taking mechanism M1 as the prior-independent optimal mechanism, which is as follows, and maximum M2 is simply offer agent 1 with price 1.5 times V2, and offer agent 2 with price 1.5 times V1. And the heuristic benchmark is just to find a linear combination of those two maxims and scale it up with the rho, which is the factor such that this benchmark is a normalized benchmark. One nice thing about this taking linear combination of those two mechanisms is that it can actually improve the performance, in worst case, the input, such that the heuristic benchmark will have gamma hat strictly less than gamma. And formally, the theorem says that for the single item two-Boyar setting with IID regular distributions, and consider the family of mechanisms to be scale invariant and incentive compatible, for the revenue maximization program, we have gamma hat to be strictly less than gamma, and the latter term is equal to beta, the prior-independent approximation factor. Okay, finally, to conclude this talk, we have given you a formal definition of the benchmark optimization program and show its equivalence to the prior-independent analysis. And we show that there is a heuristic way for finding the benchmark, and we show that this heuristic optimization is not without loss. And this is shown by solving a major open problem in the prior-independent mechanism design, which is to sell a single item to two agents and maximize the revenue of the seller. One major open question remaining for our paper is to see whether we can find a benchmark design framework that preserves the robustness of some ad hoc benchmarks. And that's all for today's talk. Thanks everyone for attending.